So beginning with this system, or with this matrix and the equivalent system, we follow the usual procedure, forming the matrix A minus lambda I, setting its determinant equal to 0, and taking the three eigenvalues in turn, plugging them into the equation, into the matrix, and multiplying that matrix by our x1, x2, x3 vector to obtain eigenvectors. Obtaining eigenpair 8, 2, 3, 0, 3, negative 1, 1, 0, 2, A, 5, 1, where A could be any constant, and solutions, e to the 8t times 2, 3, 0, e to the 3t times negative 1, 1, 0, e to the 2t times A, 5, 1. So that our solution set is as I've written it here. I won't read it to you. Since our eigenvalues are distinct, this is a fundamental set. So that our general solution to the equation is y equals c1 e to the 8t times 2, 3, 0 plus c2 e to the 3t times negative 1, 1, 0 plus c3 e to the 2t times A, 5, 1. Again, A being any number we might want to use here. We could use 0, we could use 1, we could use 738. It would still give us a general solution. So that, of course, this y is just our y1, y2 vector, from which it follows that our y1 is of the general form c1 e to the 8t, and I didn't write my 2. I'm going to make that kind of sloppy. It's 2c1 e to the 8t minus c2 e to the 3t, minus 1 times that, plus any constant times c3 e to the 2t. Now, that would seem to make c3 an arbitrary constant. But this A has to be specified in advance for reasons that will become apparent if you work with these equations for a while. Okay, y2 is 3c1 e to the 8t plus c2 e to the 3t plus 5c3 e to the 2t, and y3 is none of this, so it's just negative c2 e to the 3t plus c3e to the 2t. Now you can plug these three solutions into this form, or you can plug the general solution, this solution, and let me write out that solution. Okay, the vector form of the solution, of course, is just y equal to y1, y2, y3 equal to 2c1 e to the 8t, and I'm going to do this off camera. Okay, I've written it out. This coefficient should have been c3. Now it looks like a incomprehensible blob, but that is c3, not c2 as I had it before. And if we write these solutions into this form, here's our vector form of the solution. And if we plug this vector solution into the matrix equation, y prime equals ay, with a equal to our original matrix, again, we find that we have a solution. And I do recommend that you actually do that so you see how this a value here ends up not mattering. In the next clip, we'll look at an equation that has complex solutions for the eigenvalues. And we'll look at least one of the really important properties of complex solutions, the property being that either the real or the imaginary solution is a solution to the original equation.